So are there any questions before we get into this worksheet? Okay, so let's start the worksheet. Number one has many derivative computations, and they all require use of the chain rule. And in some of them, most of them, I will show the details for the chain rule computation, and some of them I won't. But here, for the first one, y equals x to the fourth minus 3x plus e to the x, all raised to the fourth power. Right here, we have a function to the fourth power. And we know how to take the derivative of something to the fourth power using the power rule. But what we're going to do, we know how to take the derivative of x to the fourth. We don't know necessarily yet, well, with chain rule, we don't know how to deal with an entire quantity to the fourth unless we reduce it to a single variable to the fourth. So what we'll do is let u be this inside function here, so that y equals u to the fourth. Because now we can compute the derivative using chain rule, because we can take dy du using our 4 pages of derivative rules. Dy du is 4u cubed. Du dx, we can again take the derivative du dx using our 4 pages of derivative rules. We get 4x cubed minus 3. And e to the x, the derivative of e to the x is itself. So we have our dy du, we have du dx. So we can find dy dx by multiplying these two together. Doing that applies the chain rule and gives us the derivative. So we get 4u cubed times 4x cubed minus 3 plus e to the x. And we can rewrite u in terms of x, so we should do that. U equals what? X to the 4 minus 3x plus e to the x cubed, and then 4x squared, sorry, 4x cubed minus 3 plus e to the x.
Mr. Cameron, could you label which one of these is the f is derivative of f x, and which one is the derivative of gx?
Yeah, so
Like, at
the
the
chain
bottom.
rule, yeah, we had 2 different notations for the chain rule. We had the one where we used a u substitution and wrote everything in terms of y, u, and x. The other notation uses f and g, and in that case, where do I have room on the board? In that case, I don't want to erase anything, but I don't have room to write it. I guess I'll erase this middle part. If we were to write it in terms of f and g, here, g of x would be that quantity, and f of g of x so with the other notation, g of x would be that, and f of g of x would be that up there. Any other questions about this one?
We need to go for the examples. Can you do it for like both for both ways? Because I'm having a better time understanding it through the first rather than the alternate notation.
Yeah, I will try to, and there won't be time to do all of them both ways, but I'll make mention of both ways as we go through them. But in the answer, the 2 parts of the chain rule with this notation that one is the f prime of g of x. So this one is f prime of g of x. And then just this piece over here is g prime of x. Any other questions about this one? So we'll notice here we had a function to the fourth, and its derivative was 4 times that function to the third, and then times the derivative of that function. Next, we have what? Log of cosine x. So here we have log of cosine of x, the natural log of cosine of x. So in our derivative rules, we have a rule for the natural logarithm. So what we can do is make a substitution here. Let u be that inside function cosine x, so that y is now written in terms of u, natural log of u. Then we can take dy du and du dx using our derivative rules. Dy du here is 1 over u. Du dx. So derivative of log u, 1 over u. Derivative of cosine x is negative sine of x.
Hey, Ms. Cameron.
Not really.
Is the dy and the du is that like f to the derivative
Yeah.
of x, and then the other one is like g to the derivative of x, so something like that?
Yeah, so in all of these, so the two different chain rule notations the way to compute a derivative using the two different notations requires that we multiply two different things. And in the one notation, we would have f prime of g of x, which would be 1 over cosine of x.
Wait, but why is it 1 over u? Why is it 1 over u? I don't understand where the
Because
1
we're
came
making
from.
this substitution, u equals cosine x, so that we can apply the derivative rule correctly. So if you were using the f prime notation, you would just substitute u back in, and then g prime of x would be the same, negative sine of x. But either way, the derivative of the original function is found by multiplying these two together. So dy dx is the first one times the second one. And then if we have u, we get rid of u equals cosine of x. So we get what? Negative sine of x over cosine of x. And this does, you will observe, simplify the negative tangent of x. So in these, you don't necessarily have to simplify, but it is worth observing that this one does simplify conveniently, especially if you're taking Calc 2. This one will show up toward the beginning of the Calc 2 semester. Any questions about Part B? So part C, e to the 3x tangent of 5x. Our first observation here is that we have two things multiplied together. So if we're going to take the derivative of two things multiplied together, we're going to need to apply the product rule. So the derivative here will be given by the product rule. But to apply the product rule, we're going to need the derivatives for each of these pieces. So I'm going to do them on the side, on the bottom, as side work. Now, these markers last an amazingly small amount of time. So first, we're going to need the derivative of e to the 3x. Well, the derivative of e to the x is itself. But then with the chain rule, we're going to have to multiply by the derivative of that 3x, which is 3. So the derivative of e to the x is itself, then multiply by derivative of 3x. And similarly here for the tangent piece, for y equals tangent of 5x, you want this derivative. Well, we have here a tangent function. The derivative of a tangent function is a secant squared function. It's a secant squared. We leave the 5x alone, but then we apply chain rule, multiply by the derivative of 5x, which is 5, and I'm going to write that out front. So these two derivatives, the chain rule is applied here very similarly for both of these. The derivative of 3x is 3, derivative of 5x is 5. Yes.
For the one on the left,
Yes.
the 3e to the power of 3x, shouldn't it be 2x?
No.
Shouldn't it be
Why
3e?
2x?
Because didn't you just do the power rule on it?
So
is this supposed to
this isn't the power rule, no. This is the exponential rule.
wait,
So here we have.
How did you turn it from y? How do you turn it from e to the power of 3x to the current one at the bottom?
Yeah, we applied the derivative of the exponential. So the derivative of e to the x is itself, and then we multiply by the derivative of 3. So here, this is not a power function. This is an exponential function. We have e with x's in the exponent. The derivative for that is itself, and then times the derivative of 3x. Any other questions before we get to apply the product rule?
I still don't get it. I still don't get it.
Well, so on in the derivative rules, there's a rule for the derivative of e to the x. It's the first one on page 2 of the derivative rules. The derivative of e to something, well, the derivative of e to the x is itself. So that's where that comes from. And then we multiply by the derivative of 3x, which is 3. So we, if you wanted to write a substitution here, you would let u equal 3x, or you would let g of x equal 3x. And either way, you would get that the derivative here is 3e to the 3x using the chain rule and exponential rule. So here we have a product. Derivative of a product is given by the product rule. So we need the derivative of the first, which we have here, times the second, plus the first, which I'm gonna write a little over here. So your derivative of the first times the second plus the first times the derivative of the second. I'm just gonna move the 5 out in front. And you don't have to simplify this one. Well, you don't have to simplify any of them, but you know, these do both have an e to the 3x. You don't have to worry about simplifying that. So we have the derivative of the first and the derivative of the second. Any questions about this one? Okay, next, what do we have? X inverse sine of 7x. So again, here we have a product. We have something with x's times something else with x's. So we're going to need a product rule. I forgot what I was going to say. Well, the derivative of x we know is 1. I'll just write the answer here. Derivative of x is 1. So 1 times the second plus. Okay, I just walked into this table. That camera moved a little, didn't it? Okay. Now, I have this camera on a table sitting on 3 paper boxes. So it isn't completely stable, but well. So we have derivative of the first, which is 1 times the second plus the first times the derivative of the second. So we need the derivative of the inverse sine function. So here we have an inverse sine function. The first rule on page 4 of the derivative rules tells us how to take the derivative of inverse sine something. So we'll let u be the inside. Alternatively, you would let g of x be 7x, and then f of g of x is sine inverse of 7x. With the u substitution, you would then get dy du. Derivative of inverse sine is given by 1 over 1 minus u squared, all under a square root. That's rule 1 on page 4. We didn't prove the inverse trig derivatives yet, but we will use them. The first lecture of next week, we prove the derivative of inverse sine is given by that.
Professor.
Yes.
How did you pick what was supposed to be the u?
So here, the choice of u allows us to reduce our derivative computations to our 22 rules from the derivative rules document. So here, in that document, we have a rule for taking the derivative of inverse sine of a single x, a single variable on the inside. But we don't have a rule for taking the derivative of inverse sine of 7x. So here, if we let u be this variable, now we can take the derivative of inverse sine of a single variable using the derivative rules, and we can take the derivative of 7x using the derivative rules. So the choice of u allows us to use those rules so that we can then apply the chain rule. In general, I like to think of the choice of u as being, an inside quantity. So a large quantity on the inside of a function, which here is 7x. In part C, For the one, it would have been 3x. For the other, it would have been the 5x. So u allows us, these two derivatives we took down here, dy, du, dx, are taken using the derivative rules. So the goal in making a substitution is to get back to using some of the rules on the documented derivative rules. So here, we needed the derivative of the inverse sine of 7x. That's given by this times that. So we just put that up here where we need it. So we put the 7, 1 minus, we need to get rid of u in terms of x, it's 7x. So 7x squared is 49x squared.
All right.
So we have
So
derivative of the first is 1 times the second plus the first times the derivative of the second. Yes.
how is du over dx 7? I don't understand that yet.
So here, u is 7x. So the derivative of u with respect to x, derivative of 7x, you could use the power rule on that, and you get 7 times x to the 0. Or you could just use the observation that the derivative of a constant times x is just that constant. Just walked into this table again. Okay, that didn't move the camera.
So then the u, so then whenever we turn the u to when you turn the u to du and dx, you take the derivative of u and you kind of like turn it, because I didn't.
Yeah, so right here, u is a function of x. So we can take the derivative of u with respect to x. Just like here, y is now a function of u. So we can take the derivative of y with respect to u. Any other questions? You don't have to simplify this at all. This is a fine answer. Any other questions about this one? Okay, parts E and F. Well, let's do part E first, and then we'll talk about how we can use that to find part F. So y equals cosecant of 4x. We have here a cosecant function. So to take the derivative of a cosecant function, we need the rule for cosecant. But notice we have a 4x there. The rule for cosecant applies only when it's single variable. So we will let u equal that 4x so that y is just cosecant of u. And now we can take, I guess I'll write it down here. I'd rather it down here for part F. So now we can take dy du using our derivative rules. It's negative cosecant of u, cotangent of u. We can take du dx, derivative there is 4. And then our derivative dy dx. So dy dx is the product of these two, and I'm going to put the 4 out front. So we have negative 4 cosecant of u, which is 4x, times cotangent of u, which again is 4x. So the derivative of a cosecant function is a negative cosecant cotangent, and the derivative of 4x is 4. If you wanted g of x notation, g of x would be 4x, f of g of x would be cosecant of 4x. Any questions about this one? Okay,
Oh,
next. Yes.
why is it a negative? Why is it a negative 4?
Because the derivative of cosecant is negative.
Wait, so you just did you change the order? Because sometimes that really mixes me up when you change the
Well, yeah,
order.
I usually put the numbers out in front if I can. So yeah, I just, you can multiply in whatever order you want, so I just put the -1 and the 4 together.
All right.
Any other questions about this one? So part F is this same function, but with a square root on it. So remember, a square root can be written using an exponent. This is cosecant of 4x to the 1/2. Well, we can take the derivative of something to the 1/2 in a way similar to part A. In part A, we had something to the 4th. Here we have something to the 1/2. So dy dx, we have something to the 1/2. Derivative of that is a half of them. What is it? It's 4x. Derivative of something to the 1/2 is half of that to the -half. Then you need to multiply by the derivative of cosecant of 4x, which we have from part E. So here we have a function to the 1/2. Derivative is half of them to the -half, and then times the derivative of cosecant of 4x, which we conveniently had for part C. In this case, if you did want to go through the substitution, u would be cosecant 4x, or g of x would be cosecant 4x. And then du dx is down here. And dy du is half u to the -half.
So what is the du? I mean the dy over du.
In this case, yeah, I was just a half u to the -half because it would be what? Y equals u to the 1/2. Any questions about, I guess this should all be in parentheses. That was part F. Any questions about part F? This actually does conveniently simplify a little because the 4 and the 2, the cosecant simplify to root cosecant, but don't worry about that. Part G. We have cotangent of x squared over log 4x plus 1 with base 5. So here we have a logarithm with base 5. We saw in part B how to do the derivative of a logarithm, but here we have of a natural logarithm, but here we have a different base. So how do we do this derivative? Well, before even getting there, we observe we have here a quotient. So we're going to need a quotient rule. And I'm going to start filling in the quotient rule now, and then we'll do some side. So for a quotient rule, we need what? Bottom times the derivative of the top. So I'm going to leave a gap to put the derivative of the top minus the top times the derivative of the bottom, And this is all, I should probably leave a little more space for myself. And this is all divided by bottom squared. So we need to figure out the derivative of the top and put it here, derivative of the bottom and put it here. So let's do that on the side. So first we have the derivative of cotangent. We need the derivative of cotangent of x squared. Well, the derivative, we know how to take the derivative of a cotangent function using the last rule on page 3 of our derivative rules. So if we let u be x squared, or g of x, equal x squared, then we can take dy du and du dx. So dy du, derivative of cotangent, negative cosecant squared. Du dx, derivative of x squared, is just 2x. So here, for derivative of cotangent of x squared, we would just multiply these together, and I'm going to write them up here. I'm also going to move the numbers out front so the answer looks a little better. So we need this times this. So I'm going to put the negative in the 2x first. And then cosecant squared of, I guess I need to move that a little too, of x squared. So the derivative of cotangent x squared is negative 2x cosecant squared of x squared from multiplying those two. I have room for the logarithm, I might. But we also need for this the derivative of the logarithm with base 5. Well, the derivative of a logarithm is similar, or of a logarithm with a general base is very similar to the derivative of a logarithm with the natural base, but it does differ by a constant, and I will show the details. So we have a general rule for taking the derivative of logarithm of x with base 5. X is already used, so let's use u. If we let u, u equal 4x plus 1, well then we can find dy du. Log of u with base 5, derivative of that is 1 over u, the same as the natural logarithm derivative, except we multiply the bottom by the constant natural log of 5. Du dx is 4 plus 0, so just 4. So we needed now the derivative of the bottom. Derivative of the bottom is given by 4 times that. So we have a 4 in the numerator. We have a u natural log 5. So 4x plus 1 times the natural log of 5.
Mr. Cameron.
Yes.
Why is it now a fraction? Don't you like times them together or something?
Which part?
So on this part on the
This part, the derivative of the logarithm. So dy dx over here is what? That 4 times that? 4 over u times the natural log of 5. And u is 4x plus 1. So we have 4 over 4x plus 1 times natural log of 5. And then times the top from the quotient rule.
I don't get it yet.
Which part?
So
Is it okay that the derivative of logarithm is this fraction?
uh, both of those, and the part that that I don't understand why the right side is now a fraction. So
The right side meaning up here or meaning down
yeah,
here? So
right.
this up here is a fraction because this is a fraction. And this is a fraction because the derivative of a logarithm is a fraction. So the derivative of a logarithm of anything is takes that form.
Okay.
So we have derivative of logarithm of u, 1 over u log 5, derivative of 4x plus 1 is 4. Multiply them together, we get this. And what we needed to do was put that over here when we took the derivative of the bottom.
What I don't understand here is that how did the dy and dx turn to the fraction on the
Well,
top right.
well, dy dx, do you mean the derivative of the original function or do you mean the derivative of the logarithm?
I'm not sure, but I just don't understand how the dy over dx I don't know. I don't understand how the dy and dx turns to 4x plus 1 log 5.
Dy dx is not 4x plus 1 log 5.
Oh.
Dy dx for this side work is 4 over 4x plus 1 log 5 from multiplying that and that. And then we just put that.
So what are you doing? What are you gonna do with that? The dx and dy.
Well, what we did here, this down here was all a side computation that we needed to do in order to take the derivative of the original function. So we needed, using the quotient rule, we needed bottom derivative of top minus top derivative of the bottom, and finding the derivative of the bottom gave us that quantity. So where we needed the derivative of the bottom, we put that quantity. Part H, 3 to the x cosine x. So we saw, oh, you don't have to simplify this. I probably should have mentioned, you can just leave fractions in fractions, that's fine. So in part H, in part G, we saw the derivative of a general logarithm. Here in part H, we're going to do the derivative of a general exponential. So in our derivative rules, we have a derivative of 3 to the x, but we don't have in that page of derivative rules, derivative of 3 to the x cosine x. So here, we'll let u equal our exponent so that y is now just 3 to the u. We can take that derivative, and u is x cosine x. We can take that derivative. And again, the other notation, that would be our g of x. G of x is x cosine x. dy du, we have 3 to the u. Derivative of 3 to the u is similar to the general, or to the natural exponential, but you need to multiply by the constant natural log of the base. And du dx, to find du dx, notice here we have a product. So we're going to need a product rule. Derivative of x is 1. Derivative of cosine x is negative sine of x. So for du dx, derivative of x is 1, derivative of cosine is negative sine of x. So now,
Mr. Cameron.
dy dx is the first thing times the second. And I probably should have written that a little smaller because I'm going to have to write it again. So 3 to the u, natural log 3 times cosine x minus x sine x, and u equals x cosine x.
Mr. Cameron.
Yes.
For the du and dx, where did the cosine x how come it's still there? Because you just said that the x times that is 1. So
Well,
then,
here we have u is a product, so it's x times cosine x. So for its derivative, we need a product rule. Derivative of x is 1. Leave cosine x alone, plus x times derivative of cosine x, which is negative sine. And with
yes, I still don't understand where, because I still don't understand how. Okay, so for the u equals x times cosine x. You left the cosine x by itself, but shouldn't have convert that to negative sine x. So then where's the extra cosine x coming from?
right here, this is a product, so we need the product rule. So here, derivative of x is 1, leave cosine x alone, plus x times derivative of cosine x, which is negative sine.
No, I don't get it.
But right here, u is a product of x and cosine x. So in week 5, we saw the product rule told us how to take the derivative of a product. We need the derivative of the first. Derivative of x is 1. Leave the second alone, plus the first times the derivative of the second, which is negative sine of x. Any other questions about this one? With general exponentials, I frequently do like to write out the details for the chain rule because I find them, of all of them, I find them the easiest to make a mistake on, probably because of this log 3. So we also, in week 6, we introduced higher order derivatives, taking second, third, and so on derivatives. Problem 2 here asks to find a second derivative. We need the second derivative of this function. So the first derivative, we can find in problem 1c, we saw how to take the derivative of e to the 3x. It was 3 e to the 3x. In problem C, we also saw how to take the derivative of tangent of x. Derivative of tangent of x was secant squared of x. So here we have the first derivative. This question doesn't want the first derivative. This question wants the second derivative. Well, to do the second derivative, we need the derivative of this first thing and the derivative of the second thing. Well, conveniently, constants carry through. So the derivative of 3 times e to the 3x, well, let's just cover the 3. Derivative of e to the 3x, remember, is 3 to the 3x. But if there's another 3 there, you need to multiply that by 3. So you get 3 times 3, which is 9, e to the 3x for the first part. Now, the second part is more inconvenient because of that square. So I'm going to write the answer here, and then I'm going to show the details. So for that second part, the derivative of secant squared x is 2 secant squared x times tangent x. Now, where does that come from? Well, we'll do side work. Y equals secant squared of x. Now, that looks, in its most basic sense, like a secant function. But it is actually not a secant function. It is a squared function. Meaning, we can rewrite this as a function all squared. Which function all squared? Well, it's secant of x all squared. And we know how to take derivatives of functions squared. We can let u be, in this case, secant x. If u equals secant x, well, then y is just u squared. If u is secant x, dy du, 2x to the first, 2u to the first, du dx, derivative of secant is secant tangent, secant x tangent x. Sometimes my lowercase c's look like lowercase e's. So we have a square function. We let y be the inside of the square function. Or we let y, sorry, we let u be the inside of the square function. dy du is 2u. du dx, derivative of secant x is secant x tangent x. So the derivative of secant squared x is 2u times secant x tangent x. 2 secant x, maybe I'll write that. So dy dx is 2 secant x times secant x tangent of x. And of course, secant can be rewritten as secant, can be, well, is equal to secant squared. So we have 2 secant squared of x times tangent x. So here, remember, secant squared of x is a function all squared. Any questions about this one?
Yeah. So you just said that u is to the power of 2, but when you go down to the bottom, the dy and du equals 2 times
Yes.
u. That's not the same thing as squared.
Well, these aren't the, so we have y equal u squared. So derivative of u squared is 2u to the first.
I'm lost.
Derivative of u squared is 2u. That's the power rule. And then du dx, secant tangent. And then in simplification, the 2 secants can be rewritten as secant squared. Any other questions about number 2? Okay. So number 3, in the lecture, we saw a couple different graphs of functions that weren't differentiable everywhere, meaning, the derivative is defined as a limit, and we saw earlier that the limit, a limit, doesn't necessarily exist. So if the derivative is defined as a limit, a question to ask is, what would that limit not existing look like? Or what could that limit not existing look like? And we looked at 3 different types of graphs where that derivative didn't exist. That's a lousy corner. 1, we saw a corner, derivative didn't exist there. 2, we had something called a cusp, which looks like a curvy type corner. Derivative doesn't exist there. And 3, we saw a vertical tangent. If you had a vertical tangent, the derivative didn't exist because the limits were infinite. And in the lecture, we discussed the first one and the third one in some detail. But we didn't talk much about the second one, aside from observing how the slopes of tangent lines change in that graph. But here in problem 3, we have an example of a function that does have a cusp. Now, why does it have a cusp? Well, the first thing mentioned in this question is to graph this function. Well, how do we graph this function? First, it's piecewise. So it's going to be graphed in pieces. For x greater than or equal to 0, we have root x. So that looks like that from our standard root x function. What about for the other piece, x is less than 0? Well, we have root negative x. How do we graph that? Well, we can do that using graph transformations. Using graph transformations, well, to graph that, we start with y equals root x, but then we need to make the x negative. You make the x negative, that causes the positive x-axis to flip over to the negative x-axis and the negative x-axis to flip over to the positive x-axis. We're making all x's negative, causes it to flip over the y-axis. And what does this look like flipped over the y-axis? Well, it looks like that. So for x less than 0, we have this function, and conveniently they do intersect, well, they do meet at the origin. So here we have a graph of this function. Now, what is the exact phrasing here? Show it's not differentiable at x equals 0. We're going to show, I personally like the argument using the definition of the limit. You could do a parallel argument using the power rule. I won't show that. I'm going to show using the definition of the derivative at a point. So what am I showing? So we show f prime of 0. So the question says show that the function is not differentiable at x equals 0. So we're going to show f prime of 0 doesn't exist using the definition of the derivative at 0. So the definition of the derivative at a point we saw when doing the derivative or when doing this argument with the absolute value function in lecture. So f prime of 0 is the limit. Is this going to fit? Yeah, well, as x approaches 0, of f of x minus f of 0 over x minus 0. That's the derivative at 0. And how does this simplify? Well, we can't do much simplification yet. All we can do is f of 0 is 0. 0 on the bottom is 0. So this just equals this limit. So we're going to show this derivative doesn't exist. How do we show the derivative doesn't exist? Well, we're going to show that this limit doesn't exist. How do we show the limit doesn't exist? We look at both sides. So yeah, I should have started this on this side. So I'll say which doesn't exist since which doesn't exist since what? Well, the argument is going to look at both sides of 0. I'm going to write it over here. So I have room. I'm going to write it a little higher, so I have room. Limit as x approaches 0 from the right. We're going to look at the right. We're going to look at the left, and we're going to see, well, we're going to see that infinities show up. On the right of 0, how is the function defined? Root x. How do we do that limit? Well, you can't do a substitution, but we can reduce the fraction. Because x is root x, so a root x will cancel. You're left with a root x on the bottom. And as x approaches 0 from the positive side, 1 over x will approach infinity. It's for reasons similar. I think we covered week 4, maybe it was week 3. I should be able to remember that much more quickly than I am. I believe it was week 3. We covered 1 over x with power rules, with power for limits. But either way, as x approaches 0, this will keep getting larger, so it goes to positive infinity. Well, technically, that's enough to conclude the derivative doesn't exist, but I will show what happens on the other side of 0, because the computation is interesting, I think. What happens on the left of 0? On the left of 0, f of x is root negative x. The bottom is x. How does this simplify? Well, I'm not sure with all those negatives flying around. I don't want those negatives all over the place, so I'm going to flip it over. This root negative x as x goes to 0, that's too many negatives. But if we flip it around the x-axis, well, instead of approaching 0 from the negative side, we're approaching 0 from the positive side. But also, we replace all x's with negative x's. We're left with this limit, which reduces to so the negative, I'm just going to move to the top. Root x over x becomes 1 over root x. And this limit is negative infinity because of that negative. So here we have an infinity on the right side of 0 and a negative infinity on the left side of 0. Technically, the first line is all you would need to conclude the derivative doesn't exist. But it's nice to see this because we can also see it in the graph, because the slopes of tangent lines go to negative infinity on this side of 0. Slopes of tangent lines go to positive infinity on that side of 0, and we can see that.
It's Cameron.
Yes.
So 2 things. Why does the limit go to 0?
Because we're looking at the derivative at 0.
How do you know that they need to pick 0 instead?
Why is what?
Why? How did you know you need to pick 0?
The question tells us. The question show f of x is not differentiable at x equals 0.
Okay, cool. And also going back down to the bottom right parts, bottom right.
Yes.
You flipped. You for some reason you flipped the limits to the positive 0. Coming from the right side. Why was that again?
I did that because I didn't want to think about all these negatives here, because I think that's too much to think about. So what I wanted to do was flip that over the x-axis, which we could do using a graph transformation, replace all x's with negative x's and flipping. So if x approaches 0 from the left, and you flip that, well, I guess I should say, if x is approaching 0 from the left, and you flip that across the x-axis, or sorry, across the y-axis, that's going to now approach 0 from the right. And also, in doing that, all x's become their negatives. Any other questions about this one? With these three lacks of differentiability, I will say my favorite computation is the one with the absolute value. So you can keep that in mind. So we also, when we defined the limit, we discussed how we could, when we defined the derivative, we discussed how we can interpret it as a rate of change, or as a tangent line, as the slope of a tangent line. But in lecture 7.2, we also saw how we could interpret that as a rate of change. And in particular, we saw that we can interpret the slope of a tangent line as an instantaneous rate of change. And we'll see a few applications of that across the next several weeks. But here we have the particle moves along a vertical line so that its position is given by, let's write the equation correctly. So that its position is given by that. It says up is the positive direction. That will become relevant for all of B, C, and D. So I'm just going to note over here that up is the positive direction. Part A, at what time does the particle stop? Well, in interpreting the derivative as a rate of change, we can use that to figure out when the particle stops, because something is stopped when it's not moving anywhere, when its change in position is 0, when its rate of change is 0, when the derivative of position is 0. And we call the derivative of position velocity. So in part A, particles stopped when the velocity equals 0. Well, what's a velocity? We don't have a velocity function yet. Well, derivative up here, 3t squared minus 12. We want to set this equal to 0. Add 12, divide by 3. T squared equals 4. Take the square root. With that domain restriction, we take only t equals 2. Any questions about part A? Okay, part B. On which time intervals is the particle moving upward, is the particle moving downward? Well, our first observation is that moving upward is the positive direction. Moving downward is the negative direction. So the particle will be moving upward when its rate of change of position is positive. It'll be moving downward when its rate of change of position is negative. So in particular, we need to find where the velocity is positive and where the velocity is negative. So I'll say we find where velocity is positive and we find where it's negative. Well, how do we do that? Well, conveniently in part A, we already have where it's 0. So we know on the one side of 2, it's going to be positive or negative. On the other side, it'll be positive or negative. So let's look on the left first. Velocity at 1 is 3 minus 12, which is negative. And it is negative, what, 9? You know, the actual number doesn't matter. Just the fact that it's negative is what matters. On the other side of 2, we'll pick a number like 3. At 3, velocity is, what is it? It's 15, 27 minus 12. But in particular, it's positive. So the particle is moving up on what? Well, that interval, 2 to infinity. Do we include 2? Well, I wrote that we don't. Why don't we include 2? Well, at 2, velocity is 0, so it's not moving anywhere. And the particle is moving down on what? Well, notice we have a domain restriction here. So we only need 0 to 2. At 2, we already discussed it's not moving at all. Velocity is 0. What about at 0? Do we include 0? Here we do include 0. Why do we include 0? Well, let t equal 0, you get negative 12. So the velocity is negative at 0. So with these endpoints, you do have to take a moment and consider what's going on at the endpoints to determine if you have to include them. So 2 is not included, velocity is 0. 0 is included because velocity is negative. Any questions about part B? Part C says what? Is the particle speeding up or slowing down at time 1? Is the particle speeding up or slowing down at time 3? Well, speeding up or slowing down suggests that we're looking at how the velocity is, well, we're looking at how the speed is changing. And to figure that out, we can look at how the velocity is changing. How do we figure out how the velocity is changing? How do we figure out how the velocity is changing? Well, remember, derivatives tell us that, or how we can interpret rates of change. So if we want to interpret how velocity is changing, we need its derivative, which we call acceleration. Derivative of velocity, acceleration, tells us how velocity is changing. Here, acceleration is 6t. So this one says, what happens if is the particle speeding up or slowing down at time 1? Is the particle speeding up or slowing down at time 3? Well, again, we're going to have to pay careful attention to our positive and negative direction. Because remember, these derivatives tell us how this particle, they tell us information about the direction the particle is going in. Acceleration tells us a rate of change of the rate of change. I'm going to draw a line. This is going to represent our velocity. At 2, here we're looking at velocity. At time 2, velocity was 0. What happened at time 1, which we're considering first? At time 1, well, we have over here, or you can just look at the computation directly. At time 1, velocity is negative. So there's our first observation. Velocity is negative. Oh, I'm sorry. That was a mistake. It's time 2. We're looking at velocity. Sorry, this should be a 0. We're looking at where velocity is 0 at time 2. Right here, we're looking at where velocity is 0. Well, at time 1, remember, the upward direction is positive. At time 1, velocity is negative. Velocity is down here. So I'll just say velocity at 1 is down there. But acceleration tells us which direction this particle is moving at that instant. Well, it tells us how fast it's moving at that instant. What does acceleration at 1 equal? Acceleration at 1 equals 6. It's positive, which tells us at 1, the acceleration is going in the positive direction. At 1, the acceleration is going in the positive direction. So in particular, this velocity is getting closer to 0. In particular, the acceleration is in that direction towards 0. So the particle is slowing down because its velocity is getting closer to 0 at that instant. At time 3, well, we have the opposite case. At time 3, velocity is positive, acceleration is also positive. So at time 3, we mark where velocity is 0. At time 3, velocity is positive, but acceleration is pushing in the positive direction. So acceleration is pushing in that direction. So the velocity is going away from 0 at this instant. So the velocity is going up at that instant, or going away from 0 at that instant. So the particle is speeding up at time 3. Any questions about this? So remember, velocity getting closer to 0 means that it's slowing down. Velocity going away from 0 means it's getting faster. And part D just asks to generalize this example on which intervals, it should say on which time intervals the particle movement is speeding up or slowing down. Well, velocity is 0 at 2. So again, this is going to be split at 2. So the particle is speeding up on, well, it'll be speeding up where velocity is positive and acceleration is positive, or where velocity is negative, acceleration is negative. That never happens because acceleration is always positive or 0. So we get the interval 2 to infinity, not including 2. What happens at 2? Oh, including 2, excuse me. Including 2, because the acceleration is positive at 2. Acceleration is 6t. And the particle is slowing down. Well, the only remaining points we have are 0 to 2. We're not including 2 because we included it up there. Do we include 0? Well, we don't. Why do we not include 0? Acceleration is 0 at 0. So if the acceleration is 0, the acceleration is 0, velocity is not changing. I guess I'm 2 minutes over. Sorry about that. So there is a homework assignment due Monday. Definitely practice chain rule questions. It's very important, for pretty much the rest of the semester, problems like that. The weather outside does seem like it's getting less humid as the day goes on. So I hope you can enjoy that and enjoy your weekend, and I will see you on next week.